Welcome back to Quite Basic Math, and we would continue from where we stopped in the last lesson. We are still on set theory, and we're looking at introduction to Venn diagrams. So imagine you have a sample space. Imagine you have a set. I've already seen into the future that we're doing probability too, so sorry about that. So introduction to Venn diagrams, right? So imagine a set where you have A as the only set, and you're supposed to find a solution to what the set looks like in a Venn diagram. So where the shaded portion is our solution, or our solution area, so to speak. So we have A shaded this way. Now if you have two sets A and B, take note that we are looking at A, right? Set A, just set A, which you might just see as there are some cases in some questions where they say only, not the only now, just set A is this entire region you have here. What about set B? I'm sure you know what that would look like. That means that you have set A and B. Say this is A, this is B. Your set B will just be this entire region that has B. Now if you see where I'm shading, I also include their intersection. And why is that so? Because in the intersection you still have some areas that cover that set B, the portion B. Now let's go further. Let's look at A union B. What would that look like? Let's see A union B. Now A union B. Now for all the sets I have been drawing to us, all the diagrams I've been drawing to us, you realize that I'm considering a case where there are no mutual exclusiveness. What I mean is, let's quickly take a deep dive into what the concept mutually exclusive means. Now if you have two sets and they are said to be mutually exclusive, okay, what it means is that the cardinality, or the two sets, so to speak, are actually these two sets, intersection of two sets is an empty set. What I mean is there is no intersection between the two sets, meaning that the cardinality is 0. So what we are saying is, if you have two sets that they have something in common, that is, that are not mutually exclusive, okay, what it means is that this is the way we draw their Venn diagram. So can you see the way I'm drawing them, such that A and B are intersecting, A and B. So all these are actually situations where you have a non-mutually exclusive set. So if I'm going to draw mutually exclusive sets as in a Venn diagram, this is what I will have: A and B. Look at them standing alone. So this is what I mean by mutually exclusive. They don't have anything in common. So the intersection of the two sets is an empty set or a null set. All right. So let's see A union B. Okay, what do you think I would shade? Clearly I will shade both A and B, everybody in A and everybody in B. Okay, now let's look at A intersection B. How do I draw this? So we have something like this. I'm sure this is simple. From what we have been discussing algebraically, we said that you have just what you have in their middle. Okay, and what if I were asked to draw A minus B? Don't forget what A minus B is. A minus B means all the elements of the universal set that are not in B. Okay, so that is A intersection B prime. Sorry, A minus B are all the elements in A that are not in B. Okay, before we do this, let's quickly look at A complement. Okay, so we can follow through with what we did algebraically. So let's look at A complement, considering two sets that are not mutually exclusive. So A prime or A complement, what does that mean? How do we draw that? You know that this means that all the elements in universal set but not in A, or you can write it as universal set intersection A prime, right? So how do we draw that? Don't forget, we are considering a case where we have don't mind my box. Considering a case where we have two sets A and B, universal set outside. So if this is saying that if we want to find A complement, that is all the elements in the universal set apart from what? Apart from A. So I will shade everywhere. In fact, I will shade B as well, but I'll be careful enough to not shade A. Can you see that A is left unshaded? So this is actually A complement. So likewise, B complement will be something like that. B alone would not be shaded. Every other part would be shaded. Please take note of how I'm shading. I did not shade their intersection because in their intersection there are elements that will be in A. So we seriously don't want A at all, but every other thing in the universal set. So what do you think A minus B would look like then? I'm sure you have an idea of A minus B. A minus B is considering all the elements in A but not in B. Now this is where they have their intersection. If I write AB, right? So I only shade this part. So that's like saying A only. A only. So when you see a question where they say A only or something only, this is what they are talking about. Okay, talking about the elements in A that are not in the other one. Alright, so let's see. Let's keep seeing what this Venn diagrams connote. Why not let's try A and B only. Let's try B only. What would B only look like? Sorry. What would B only look like? That would be something like this is B minus A. Do you agree? This is B minus A. Alright, intersection is commutative. Please take note of that. Okay, so if I have A intersection B, it's the same thing as B intersection A. Intersection is a commutative, and union as well is commutative. A union B is the same thing as B union A. Please take note of that. Okay, so if I have A and B, set A and B, guided by universal set, to find A prime intersection B or A complement intersection B, it means that I want all the elements in B but not in A. So I will shade B only. Okay, because if I shade this middle, which is supposed to be part of B, it has A as well. Meanwhile, we don't want that, so it is B only. Okay, now let's see another point. Let's shade this. Let's see what this would look like. What about A prime intersection B prime? Now this is the same thing as A union B all prime, which you will see very shortly when we prove the De Morgan's law. Okay, so you have A prime intersection B prime, which is the same thing as A union B all prime. Now you agree with me that this means that all the elements in the universal set except in their union. I'm sure you have an idea of what that would look like. That would simply be all the people outside. So if this is A and this is B, we don't want everybody in A union B, but we want the remaining guys outside. Okay, remaining guys in the universal set. So these are the questions where you hear something like neither of the people that did nothing, the people that had neither, something like that. So we're talking about the people outside of your set. Okay, moving on. Let's see what more we can do. What if you have, now let's look at some strange kind of sets. Look at this. What about A prime union B or union B prime? A prime union B prime. Now this is under De Morgan's law. Actually, this is the same thing as A intersection B all prime. All right, you will see very shortly. You can even look at it by inspection. When you have A intersection B all prime, if this prime is supposed to attack, if you open this bracket like we'd say in algebra, and this prime is supposed to attack every one of these guys, it means that it will attack A, it will attack B. However, when it attacks this operation, it flips it. So more like if you have plus becomes minus, if you have minus becomes plus, something like that, a negation. So you should also take note of this fact. We'll see very shortly in even De Morgan's law that when you take the complement of a set, you have that set back. Okay, if you take the complement of a set, you have that set back. Let me use another sign. Okay, rather than just C, you have that set back. So please take note of these laws. All right. Now they have names. We have idempotent laws, but we're not going deep into that. If you really want to know the namings, the laws, you want to know it, you want to learn set theory in a holistic manner, you might consider putting that down in the comment section. We could schedule a live session, a paid tutorial live session if you care for that. All right. So moving on. Let's look at something quite interesting. If you now have, yes, we're looking at this guy. So how do we draw this man here? How do we draw this here? Okay, I'll give us next 1 minute. So quickly, I'll try to see what that would look like. So do DIY, try what that would look like yourself. All right, so to know what that would look like, you have something like this. You have your A and B that are exclusive. Okay, so you have something like this now. It says that I want every element in the universal set, but I don't want the intersection. So that means that I will shade every part of my Venn diagram and I will exclude what I have in their intersection. So this is what your Venn diagram would look like. Alright, so I think that's enough for Venn diagrams. Now this could also go into 3 sets. You could have it in 3 sets. For example, if you have A union B intersection C and so on and so forth, you can always draw that. But before I go into that, let's quickly talk about De Morgan's theorem. So when we are done with De Morgan's theorem for 2 sets, then we'll look at 3 sets Venn diagram. Alright, De Morgan's rule of theorem. We'll look at 3 sets Venn diagram, and after that, we would quickly, before the time is up, we'll look at how we can basically evaluate some particular sets that are not so direct. I mean, evaluating some sets giving conditions, because there are some questions that basically are interested in the cardinality and not necessarily the elements of the set. So we'll look at how to evaluate those sets. For example, the cardinality A union B. How do we evaluate this? Given some cardinalities, the cardinality of the universal set itself, the cardinality of its intersection, and so on and so forth. And we'll see how all of these guys relate to one another. And you can also use these Venn diagrams to actually see or prove or disprove each one of these equations. But let's quickly look at De Morgan's rule very quickly. Let's look at De Morgan's rule. Now for your De Morgan's rule, we want to quickly show that we want to prove rigorously. We want to prove, okay, what are we proving? We want to prove that A union B complement is the same thing as A complement intersection B complement. I also want to prove that A intersection B complement is the same thing as A complement union B complement. So we want to basically prove this, guys. For the purpose of those that might actually want to be interested in knowing how to solve De Morgan's theorem for 3 sets and also know how to draw the Venn diagrams for 3 sets, you can always schedule a live tutoring session. You should just put in the comment section and I would attend to that. Tell you how to go through the procedure. Alright, now to prove or disprove this guy, so let's start with the first one. You know the way we work in proving. So you are going from the left hand side to the right hand side, right? So you have A union B prime to be equals to A prime intersection B prime. Okay, so let's see how we can prove this guy. Now the first thing is, since we are going from the left hand side, so you write left hand side A union B complement. Okay, so the first thing is you have to, since we are talking about a set, it's important that we talk about the element. So let X be an element. The first thing to do is to let X to be an element of this set. This is a set, you must know that. Forget the fact that you have a complement. This is a set on its own. So A union B or complement is a set. So the first thing to do is to let X, let's assume an arbitrary element to be an element of this set given. Now if X is an element of the complement of the set A union B, it simply means that X would not be an element of the set A union B. I come again. If X is an element of the complement of the set A union B, simply means that X will not be an element of the set A union B. I believe you understand that. It's just, I mean, quite basic algebra. If X is an element of the complement of a union of 2 sets, then X is not an element of their union, right? Okay, so if X is not an element of their union, it means that X is not an element of their of A, and or, all right, X is also not an element of B. As a matter of fact, there's no even need to put and or. If X is not an element of the union of 2 sets, you agree with me that X cannot be an element of A and also cannot be an element of B. Remember that we said A and remember that we said that union means bringing two sets together irrespective of what they have in common. So if we say that X cannot be found in the union of two sets, it means that X cannot be found in A and X can also not be found in B. So if X cannot be found in A and X cannot be found in B, it means that X can be found in A complement. I believe you understand this. If X is not an element of A, simply means that X is actually an element of A complement, because A complement is the set as a universal set but not in A. Now if X is an element of A complement, that means that X will also be an element of B complement. Now you need to take note of these transitions. I come again, if X is not an element of A and X is not an element of B, simply means that X is an element of A complement and X is an element of B complement. Now if this is true, it means that X is an element of A complement. Now if we say and, if it is and, we use and to represent, we use intersections to most times represent and because it's combined, it has a combining effect. So okay, so we are looking at the fact that if X is an element of A prime and X is an element of B prime, it simply means that X will be an element of A prime intersection B prime. And once you look at this guy, you see that you already have what you have on your right hand side. So we are proving, this implies that A union B all prime is actually equals to A prime intersection B prime. So we have proven this, that's the Morgan's rule for the first one. Now let's look at the Morgan's rule for the second one. Now the second one says that A intersection B all prime equals to A prime union B prime. So let's see once again from the left hand side. Now while trying to prove this, some people prove from the left to the right and then from the right to the left. I feel like that is quite unnecessary. You might want to do that to show that it is truly correct, but I feel that's unnecessary. If you are given what's called an equation and you prove from left to right, you have as well proved that it is correct. You prove from right to left, fine. So you can as well prove from right to left. Are we interested in that? Okay, let me see. Let's do that. Just to fulfill all righteousness, okay? Now, if you're going to prove from right to left, let's see from right to left, what would that look like? Now, from the right hand side, if you do the same thing that we did for the left hand side. So you say let X be an element of A intersection B, A prime intersection B prime. Now, if X is an element of A prime intersection B prime, you agree with me that this means that X is an element of A prime and X also is an element of B prime. Now, if this is so, this means that X is not an element of A and X is not an element of B. Okay, if this is established, this means that X is not an element of A intersection B, and if X is not an element of A intersection B, it simply means that okay, so we said and here. So if X is not an element of A and X is not an element of B, is we can also say that X is not an element of, sorry, let me quickly do this. So yes, so we said that if X, you just look at where you are going to and then use that to guide you through to how you get to that place. Since we are going to union, right? So if X is an element of A and X is an element of B, it simply means that we can say X is not an element of A union B. You can use and or here, okay? So that means that X will be an element of A union B all prime. And this is the left hand side. So we have gone from left to right and right to left. All right, so like I said, this is just to me unnecessary. Okay, once you can go from left to right, you are proving it. So let's look at the second let's quickly look at the second law for two sets that are not mutually exclusive. So if you have A intersection B prime, so we want to prove from left to right that this is the same thing as A prime union B prime. So from left hand side is A intersection B prime. So what do we do? So you say you let X to be an element, like we start, of A intersection B all prime. Okay, now if this is true, this means that actually X is not an element of A intersection B. If X is an element of this, that means X is not an element of this, of what you have in the bracket. So if X is not an element of A intersection B, it means that X is not an element of A and X is not an element of B. Sorry, it means that X is not an element of A and X is not an element of B. Now if this is established, this means that X is an element of A prime and x is an element of B prime. Now if x is an element of A prime and x is an element of B prime, you can put and or here. It means that x is an element of A prime union B prime, and we have gone from left to right. So we are proving that the left hand side is actually equals to the right hand side. So that's proven. So that's that about De Morgan's rule. So you can go over it again if you find it quite confusing, or just drop in the comment section your questions. Now moving on, let's look at something finally as we conclude this lesson. Now if you have to evaluate the cardinality of a set, imagine you are given imagine you are given some cardinalities, say n of A. You are given n of A in a question, you are given n of B in a question, or whatever it is you are given in the question. You are given the cardinality of the intersection, and then you are asked to evaluate something, as the case may be. So you need to know these equations. The first one is when you are given your universal set is actually equals to the cardinality of A plus cardinality of B minus cardinality of A intersection B plus the cardinality of the people outside, which is A prime intersection B prime. Okay, just check the Venn diagram to see what this means. Don't forget that this means A union B all prime, that is the people outside. This is your universal set in a case where you have some people outside. Okay, and then your A union B, okay, is simply what you have here. All you have here is A union B, so which is equals to n of A plus n of B. This equation is very important. This is the most important equation when it comes to the union of two sets, the cardinality of the union of two sets. And even this equation is used in probabilities. Okay, so in evaluating probabilities. So take note of this equation very well. The union of two sets can be evaluated as the individual cardinality of those sets minus their intersection. Now if you don't go now, this equation can also be reduced to this. Now if A and B are mutually exclusive, that is you don't have anything in common, their cardinalities is 0. If A and B are mutually exclusive, this equation will become something else. And what was that? Let's quickly see. If A and B are mutually exclusive, that means that the cardinality of A union B will actually be equals to just n of A plus n of B, because this guy will now become 0. I hope we understand that analysis. So this will become 0, right? So n of A union B will just be n of A plus n of B. Now let's look at some other ones. Now what about n of A? Let's look at n of A union B again in another form. Now let's assume that I don't want to go through this route of taking the individual ones. What if I want to take only, this is n of A, that is the entire A set. What if I want to look at the cardinality of just A alone? What I mean is this. Remember I call this A only or A alone, whatever you may call it, this one, where I have to just shade what is in A alone, or like shading the entire A. So what if I want to look at that and I want to use it to define A union B? That means I will have A only plus B only. Alright, this equation also works, plus their intersection. Now this guy also can be used to evaluate the union of two sets. This equation could also be used to evaluate the union of two sets. Please so take note of that very, very carefully. Alright, and then also, what if we have three sets? I'll just give us the equation of three sets, and then we would end this particular lesson. So next lesson, you should prepare for problem exercises. We'll look at as many questions as possible. We'll try and solve them. When we are done with that, we would call the set theory quit. Call it quit, and then we'll look at partial fractions, indices, and logarithms, which will be lesson 2 of the module 1 of the fundamentals to university mathematics. All right. So let's look at three sets. Imagine you have given sets A, B, C. So imagine you have three sets A, B, C that are given set A, B, C, which are non-mutually exclusive, which are not mutually exclusive. What I mean is that there is an intersection between the three sets. How do we write their union? Okay, because there are some questions that you would simply need that equation. All right, so how do we go about that? Okay, so you have this. This is what I'm saying. In Venn diagram, imagine you have this A, B, and C. So if you look at this Venn diagram carefully, you would see that there is an intersection between the three sets. Okay, so how do we evaluate this? So in this case, your n of A union B union C would actually now be equals to n of A plus n of B plus n of C minus n of A union B minus n of A union C. Sorry, not union, pardon me, the intersection please, not the union. So A intersection B minus n of A intersection C minus n of B intersection C plus n of A intersection B is quite similar to two sets actually if you look at it very carefully. Then yeah, this would be your union of the three sets. So union of three sets is simply the addition of all the individual sets, subtracting the individual intersections and adding the entire intersection of all of them together at once. So this will be the union of three sets. Okay, that would guide us to solving questions as they come one after the other. All right, so before we proceed, let's quickly look at a simple question that involves two sets actually. But before I do that, I would like to quickly talk about something that I omitted so far. I've not mentioned it. Now there's another symbol, or there's another operation, or how do I put it now? There's something you need to learn about sets, which I haven't spelled out for us, and that is the idea of subsets. I know I've mentioned that the power set or the power of a set is the total number of possible subsets in that given set, but actually, what does a subset mean? What do you really understand by subset? Now, your subset could either be proper or improper. Okay, could have proper subset or improper subset. Okay, as the case may be. All right. So, what do we understand by subset? So, subset is just trying to say a set of another set. That is, you have a set, right, that houses another set. So that is too much grammar. If I say A equals to 1, 2, 3, and imagine your B is equals to 2, 4. Now, 2, 3 rather. Now, if you look at this carefully, it looks like what you have in B can be found in A. We can say here that B actually is a subset of A. Now, B being a subset of A here, okay, all right. So B is a subset of A. However, this is not just A being a subset of A. Okay, so this is actually B is actually a proper subset of A. And how do we know the difference between proper subset and just a subset of something? Now that is quite tricky, and this is where a lot of people miss it. Now you could say B like this A or B like this A. Now let me tell you the difference between the two. Now if you say B is a subset of A, which is what you have here. B a subset of A is what you have here, but proper subset is saying that, which is actually a proper subset, not just a subset. It's actually a proper subset. Now, proper subset is saying that what you have in B can be found in A, but B is not equals to A. Did you see that? What you have in B is in A, but B is not A. Now, if you have B to be a subset of A, it actually means that what you have in B is actually A, or you can say there's a possibility that B is actually equals to A. Now that's the difference between subset and proper subset. So it's important that you know that a set is actually a subset of itself. I mean, you agree with that, because yes, a set is a subset of itself. And then you must also agree with the fact that that's why I said that a null set is a subset. It's actually a subset of every set, no matter what it is. A null set is a subset. That's why we're able to list a null set to be one of the possible subsets of the power set. I mean, one of the possible subsets of a given set A. That is, your empty set is one of the sets that you have whenever you are listing a set, as the case may be. All right, so let's look at something. This is getting clumsy. Let's quickly look at what I'm saying here. So I believe you understand subsets, proper subset now. So let's look at a very interesting question, probably that would help us understand what I'm saying here. So if I say that A is a subset of B, okay, if I say A is a subset of B, all right, and I take its complement. Now take note that just like in intersection and union, if I take the complement of this, it will change the sign. Now there's something called subset. This like C, looking like a C that is lying flat, represents subset. Now if I change the direction of how the C is lying flat, more like something like this, then I have a superset. So we have something called subset and we have something called superset. This is subset, this is superset. So subset, you understand the idea of subset. So if the rows were changed, so if I say A is a subset of B, this implies that B, on the other hand, will be a superset of A. I come again. If A is a subset of B, it means that B is a superset of A. That is, B swallows A. B swallows A. That is, B actually houses A. That's the idea. Okay, so in a case where A is a subset of B, now take note of this. If A, take note of this. If A, I'm coming back to this, please. If A is a subset of B and B is also a subset of A, it can only mean one thing, and that is the fact that A is actually equals to B. So this is another condition of equality of a set. So another condition to know the quality of a set is that if they are if they are subsets of each other, that means that the sets are actually equal. So if A is a subset of B and B is a subset of A, it means that A is actually equals to B. So take note of that. Now if A is a subset of B, complement, okay, if A is a subset of B, complement. Now you might be thinking in your heart that I said this sign means proper subset, that why am I now interchanging it? So take note of something. Sometimes the subset idea and the proper subset idea are used interchangeably. Sometimes they are used interchangeably, but you must also take note of something, that if I don't put the sign here, okay, if I don't put the sign here, that means that there's no probability. If I just write it like this, it means that they are not equal in that sense. So most times they are strictly not equal, but once I now put the sign here, it means that there's a possibility that they are equal. So that's the point. It's just an idea of inequality too. It's like analyzing inequality. A few weeks from now, I should drop on the mastering basic algebra inequalities, so that some of us can be able to catch up on inequalities. All right, so let's go back to what we're saying. Now if I take the complement of this expression, it will change the operation. That means that from being a subset, that means that A will now become a superset. Once I can open the complement, this is what will happen to it. So unlike union and intersection, where the complement will now come inside, the complement is not in that sense coming inside. You will just have this at the end of the day. Okay, all right, and we agree with this, that if A is now a superset of B, that means that B will be a subset of A. So we can see what the complement has done to this operation. All right, so if you have really learned anything so far in the course of learning set theory, please comment that in the comment section, and also do well to share this video to your friends that might also need help with set theory, understanding these basics of set theory and knowing how to analyze given sets. Next lesson we would look at how to solve questions and as many problem sets as we can solve. Thank you for your time. Quite basic math.